Hello students. Today we'll be going through the last session or the last lecture of the chapter of coordination compounds. So today we will basically draw the conclusion to a chapter that we have been discussing throughout the last 1 month. So today we will focus our discussion mainly on the crystal field theory, which is the most important part in this coordination compounds chapter. So in this class, we will basically talk about the crystal field theory, its application in determining the geometry of the compounds, their magnetism, their colors, and etc. And lastly, we will talk a little bit on the metal carbonyl compounds, and then we will conclude. So we shall start. So in the last class, I have told you about the crystal field theory. Now if I'm going to go do a recap of the last class because it will be helpful for you. In this crystal field theory, it's actually an electrostatic model which considers the metal and ligand bond to be completely ionic. So let me write this for you. The metal and the ligand bond, that is the bond between the metal and the ligand. M stands for metal and L stands for ligand, is assumed to be completely ionic, and which is arising purely from the electrostatic interactions between the metal and the ligand. Now ligands are actually treated as the point charges. Ligands are treated as a point charges. In case of anions, point dipoles in cases of neutral molecules, and point charges in cases of anions. Now we have 5d orbitals. You know all of them. That is dxy, dyz, dzx, dx square y square minus y square, and dz square. So these are the 5d orbitals. Now you can see here the 5d orbitals are degenerate. Now degenerate means they all have the same energy. So if we are writing these 5d orbitals in the same energy, suppose in this format, if this is the energy axis, so you see the 5d orbitals are lying on the same plane. That means they are having the same energy. The same energy is actually written in terms of degeneracy. That's why they are called degenerate. Now, in case of an isolated gaseous metal atom or ion, which metal atom is gaseous in nature and it is isolated, that means it does not fall under an influence of any of the ligand. So solely suppose a zinc atom or zinc 2 plus ion is sitting lonely and no other ligand is there. That's when it is called the 5d orbitals are degenerate. Now the degeneracy is maintained if a spherically symmetrical field of negative charges is surrounding the metal atom. Now you can see here the degeneracy is maintained if a spherically symmetrical field. Suppose we are talking about a metal and it is surrounded by a spherically symmetrical field. Suppose you are having this negative charge over here that are spherically surrounding the metal atom or ion. Then this degeneracy of these d orbitals is maintained. That means all the d orbitals will remain in the same energy. Now what happens when the ligands will come and distort the spherically symmetrical field? Now whenever this negative field is generated due to presence of ligands, you can see the ligands over here. It's ammonia or hydroxide or any other ligand you can talk about. When the ligands are there, so they will interact by their negative dipoles with the metal atoms or ions, and then the spherically symmetrical field becomes asymmetrical. So then you can see when the metal atom were having symmetrical field, now in presence of ligands, the field will be now asymmetrical. So from this we are coming to this. This is a distorted, or you can say asymmetrical field. Now this spherically symmetrical field have now become distorted. So when this distortion comes in the electron cloud surrounding the metal atom, then this degeneracy is not present there. That is called the lifting of the degeneracy, and the result being the splitting of the d orbitals. Then in presence of the ligands, the field becomes asymmetrical, the d orbitals get splitted. Now the pattern of the splitting actually depends upon the nature of the crystal field that is provided by the ligand. So depending upon the nature of the ligand, the distortion in the spherical field will occur. Then the splitting of d orbitals will be occurring on different modes depending upon the ligand. So we are having three such scenarios mainly: octahedral, tetrahedral, and square planar. So these are the three main crystal fields that we'll be discussing in this case. Depending upon the nature or the number of the ligands, the spherical field around the metal ion will be distorted, and then the lifting of degeneracy will take place and the d orbitals will be splitted. So according to the nature of the splitting, we are having these three geometries around the metal ion. First one is the octahedral, which is the one of the most common geometries. Then we are having tetrahedral, and then we are having square planar. These tetrahedral and square planar geometries are having coordination number 4. These two are having coordination number 4 around the metal center, and the octahedral geometry is having coordination number 6 around the metal center. So now we will move towards specific cases, mainly octahedral and tetrahedral, to discuss their crystal field splitting in the coordination entity. So this is typically the picture that is describing the splitting of d orbital in an octahedral crystal field that I have drawn. Firstly, you have to have a clear look at that, like how it is splitting. So we shall start with the basics. So we shall start with the left hand side. So firstly, you see the axis that is drawn in the y-axis. It is nothing but energy. So in the y-axis, we will talk about energy that is actually going from top to bottom in higher side. And you can see here the metal d orbitals are present. You can see 5 metal d orbitals over here. And if we can think of this is an x-axis, this the background, it is the y-axis, and in the line of the energy, it is the z-axis. Now, firstly, this is the metal atom which is isolated and in the gaseous phase. Now it is actually under the impression of a spherically symmetrical field. So symmetry is maintained till here itself. It is the spherically symmetrical electric crystal field around the metal center. So in this octahedral coordination entity, we know the coordination number is actually 6. So 6 moles of or 6 atom of L will come and surround the metal ion. Now there should be a repulsion between the electrons in the metal d orbitals and the electrons of the ligands. So ligands are having the electrons. There are also electrons present in the metal d orbitals too, and there will be a repulsion. Now such a repulsion is more when the metal d orbital is directed towards the ligand. Now these metal d orbitals are present and we are having these ligand electrons also. So when we are having these ligand electrons and when we are having these metal d orbitals and when they are having or they are lying on the same axis or they are on the same orientation, then this repulsion will be quite high because the repulsion will be head on. But when the ligand, then when the metal d orbital does the dx square y square and the dz square, these orbital which point towards the axis along the direction of the ligand will experience more repulsion and will be raised more in energy. Because you see here, if we can draw this octahedral like this, we're having this metal dx square y square and dz square on the ligand direction only, axis only. That's why their energies will be lifted more. Here you can see the dx square y square and dz square are there. But when the ligand axis, but when the orbitals which are directed between the axis, now they will be lowered in energy. So we are having this way the x-axis, this is the y, and this is the z. Now since this x is here, on the x is on this direction, y is on this direction, and z is on the above. Now since these are actually lying between the x and y, that's why they are termed the xy. Xy means the plane between x and y. So between this, yz means between y and z, and zx orbitals be between z and x. So when the orbitals are actually directed between the axes, then they will be lowered in energy relative to the average energy of the crystal field, because they are experiencing less amount of repulsion. Now, if I can start from the beginning, we are having this free metal ion over here, which is having 5 d orbitals, namely dxy, dyz, dzx, dx square y square, and dz square. Now, in presence of a spherically symmetrical magnetic field, the energy will be lifted, but the degeneracy will not disappear. It is there. You can see the 5 d orbitals are still there. And the midpoint of this energy is termed as the barycenter. Now, with respect to this barycenter, when the ligands will come closer to the metal atom and will experience repulsion from the metal d orbitals, then the orbital's energy will be splitted. Then the splitting of the d orbital will happen. You can see over here, it is the average energy of the d orbitals in a spherically symmetrical field, and here the splitting has happened of the d orbitals in the octahedral field. Now this splitting is quite interesting to have a notice. You can see here, as I have said, the dxy, yz and zx, the orbitals that are actually pointed or directed between the axes, so their energy will be lowered to the average energy. This is the average energy point, and you can see the dxy, yz and zx, these 3 orbitals energy will be lowered. So they are termed as the T2G orbital. This G suffix is actually coming from the name gerade. It's a German word, and it means the having the point of symmetry. In case of octahedral complex, the point of symmetry is actually denoted by this letter small I. This small I, or this point of inversion, or you can say the center of symmetry, is such a point from which if you can go to one direction, we will find the same in the opposite direction. Then this complex will be termed as the having a center of symmetry. Then it is having to set this I. You can see from metal, if we can go on this direction, we are having this L. If we go the opposite direction, we are also having the L. From metal, if you can go to this direction, we are having L. In this opposite direction also, we are getting L. And likewise, in this axis also, we are getting L over here. In the opposite direction, or in the 180 degree, we are also getting the same L. So that is actually meant by the center of symmetry, or you can say I. So when the complex is having the I, or the center of symmetry, then the suffix G actually comes into picture. That's why the orbitals are actually denoted here by the notion T2G. And when the orbital's energy, when they are actually increased, the energy is lifted. So these lifted 2d orbitals are termed as EG. So we are having 3 T2G orbitals and we are having 2 EG orbitals. Now, since the average energy of the complex should have been the constant, here the average energy was something. Now we have splitted the energy orbitals into two segments, 3 T2G orbitals and 2 EG orbitals. Now what will be the energy of each orbital? That is actually quite interesting to know. Here you can see we are having 5 orbitals. And the gap between this T2G and EG orbital is termed as the delta O, where the O stands for the octahedral geometry. Since we are talking about an octahedral complex, that's why it is termed as the delta O. Now this delta O is nothing but the crystal field splitting energy. Since the degeneracy has been removed due to the ligand electron and the metal electron interactions or the repulsions, so we are having 3 T2G orbitals of lower energy and 2 EG orbitals of higher energy. Now the splitting of the degenerate levels in presence of ligand is termed as the crystal field splitting. The crystal field separation energy is denoted by delta O that I recently said. The O stands for the octahedral geometry. When we will talk about the tetrahedral one, it will be termed as the delta T. When we will talk about the square planar one, we will be writing it as delta SP. So let's bring back to our old discussion, which is this delta O. So what is about this delta O or the octahedral geometry or the crystal field splitting energy? Now we are having these 5D orbitals where we have broken them in 3 T2G orbitals and 2 EG orbitals. Now what will be the average energy? Let's say the average energy here was some 0. So basically how this has been splitted, their net energy should also remain 0. That's why when we are having 3 T2G orbitals, their average energy was termed as the 2 by 5 multiplied by delta O. And when we are having 2 EG orbitals, their energy is treated by 3 by 5 delta O. Now, since the energy is actually downward for the T2G orbitals, so actually the energy is actually less for 2 by 5 delta O. The gap between these two, or the gap between this T2G and the barycenter is actually typed as delta O. And from the barycenter, if you can go upward, it will be having 3 by 5 delta O. Now between these two, this one is the energy of T2G orbitals and these are for EG orbitals. Now since the total energy should be same, now we are having 3 T2G orbitals. So if we multiply 3 into 2 by 5 delta O, and then we are having is addition total the EG orbitals, we are having 3 by 5 delta O. Now since their energy is actually on opposite direction, this T2G are having energy downwards and EG is having energy upwards. So if we can think of one of the orbital energy as positive, then automatically the other one will be termed as negative. So let's say this EG is actually negative. So then we are having 2 into minus 3 by 5 delta O. Delta O being common, we'll write it on the outside. Now since we are having 6 by 5 plus minus 6 by 5, total it will be 0. Hence the net energy is maintained. That's why the separation has been thought of in this procedure. Like 2 EG orbitals will have 3 by 5 delta O energy and 3 T2G orbitals will have 2 by 5 delta O energy each. That's how the entire symmetry of the energy or the conservation of energy is maintained over here, so that the total energy added is actually equal to 0. So that is all in this case, the crystal field splitting. So firstly, if we can do a recap on the metal d orbitals were there, which is of a free gaseous metal ion. Now, in presence of a spherically symmetrical field, the average energy is actually quite above from the free metal ion, and the midpoint is termed as the barycenter. Now, in presence of the ligand field, when the ligands will come closer to the metal atom or ion, then the orbital's energy will be lifted. One will be lifted, another will be dropped. So degeneracy will be lifted and the splitting of the orbitals will take place. So we are talking about these low-lying orbitals 3, which are T2G, and we are having the high-lying energy, which is EG. 2 EG orbitals, dx square, y square, and dz square, and 3 T2G orbitals, which are having the energy 2 by 5 delta O, dxy, dyz, and dzx. Now this delta O, or that is the crystal field splitting energy, is a unique thing, which is solely produced by the ligand and the charge on the metal ion. Now, depending upon the nature of the metal and the nature of the ligand, the difference or the separation between the T2G and EG will be determined. So, to account for the statement like which ligands will produce high delta O, so we are having a gap between the T2G and EG. So, the gap between T2G and EG is termed as the delta O. Since we are talking about an octahedral complex, so it is a delta O. Or you can say generally delta, that is the crystal field splitting energy. Now, depending upon the nature of the ligand, the splitting of d orbitals will be determined. Now, there is a popular series which is termed as the spectrochemical series. So, I would suggest you to rather go through this series, that this series tells which one is able to split T2G and EG more, and which is able to split T2G and EG less. Now, depending upon the spectrochemical series, we will say which ligand is actually strong field ligand and which ligands are weak field ligands. So, in the spectrochemical series, the low-lying molecules are actually the weak field ligands. The higher ones are actually strong field ligands. These are actually strong field ligands. These ones are actually weak field ligands. And the ligands which are lying midway are termed as the moderately strong field ligands. So these you can see, have a look at the ligands spectrochemical series, which is starting with iodide. It's I minus less than Br minus less than thiocyanate, which is SCN minus, less than chloride, less than sulfide, which is S2 minus, less than fluoride, less than hydroxide, which is less than oxalato, which is C2O4 2 minus, less than water, less than NCS minus. So here you can see SCN minus and NCS minus are actually two different, same ligand of an ambidentate ligand series. So in SCN minus, it is binding towards the S center, which is binding towards the S center. So when it is binding through SCN S center, it is a weak field ligand. That's why SCN minus is actually in the lower end of the spectrochemical series. But when the same ligands, another ambidentate form, which is NCS minus. So NCS minus bind through the NN. So this is actually moderately stronger field ligand, NCS minus. So depending upon the nature of the atom which is binding to the metal center, the field strength of the ligand will be determined. So here you can see let's again talk about the NC. Then we are having this EDTA 4 minus. Then it is less than of that of ammonia. Then it is then ethylene diamine, and then we are having extremely strong field ligands, which are thiocyanate, which are cyanide, CN minus, and lastly we are having CO, which is the one of the most strong field ligands in the spectrochemical series. Now this is an experimentally determined series which is based on the absorption of light by complexes with different ligands. How this series gives valuable information about the variable field strengths of different kinds of ligands. Now this, if we can remember this series will tell you which one is the strong field ligand, which one is the weak field ligand, which ones are moderately stronger field ligands. Now, depending upon the nature of the field strength of the ligand, the octahedral splitting will be determined. Now, we are having mainly assigning the electrons. Now, obviously, the electrons in cases of D2, D3, the D electrons will occupy the T2G orbital singly in according to the Hund's rule. So when the degeneracy has been lifted, we are left with 3 T2G orbitals and 2 EG orbitals. Now, when we are talking about this D1 to D3 system, then the electrons will be occupying the T2G orbitals 1, 2, and 3. There is no need of this crystal field splitting scenario, because then the electron fulfillment will be according to the Hund's rule. It will not be violated even. But whenever we are talking about this D4 to D7, these electronic configurations, when we will talk about D4 to D7, when the EG orbital, when there will be two different options. So these ones are T2G and these two are EG. Now let us assume a specific case of D4 ion. So let's talk about this D4 ion, how the electrons will be occupying the levels. Let's say we are having the first case, two possible scenarios will occur of electronic distribution. In the first case, we will first fill the electrons according to the Hund's rule 1, 2, and 3. But when the fourth electron will go, that will be actually generating two different possibilities. The fourth electron might be pairing with the T2G orbital itself, and we are not left with any electron in the EG orbital. Here also, we are filling the T2G by 1, 2, and 3, and the fourth electron, rather being pairing with the present T2G orbital, it will go to the EG orbital. So here you can see the two different factors will be there. First one is the delta, and second one is the pairing energy. First one is the crystal field splitting parameter, and the second parameter is the pairing energy parameter. So what will be the relation between these two? Whether it will be greater than equal to, or whether it is less than or equal to. According to these two possibilities, the electronic configuration will be determined. Now the pairing energy is actually representing the energy which is required for electrons pairing in a single orbital. You see two electrons are actually here paired up. So when the delta is actually high or greater than the pairing energy, then the pairing will occur. Because for pairing, less amount of energy is actually required. Now when delta will be high, the delta will be high in case of the strong field ligands. And when this delta is actually less in energy than the pairing energy, when delta is less, the pairing energy is more, then the electron, the fourth electron, will not pair up with the present electron because it is high energy. High energy is required to actually pair up the electron. Since the delta is low, so the barrier is less, then it is easy for the fourth electron to go to the EG level than to pair with the T2G electron. So in that case, when the delta is less in case of the weak field ligands. which cannot split the T2G and EG more. So now we have come to the conclusion, when the ligand is a strong field one, then delta is greater than P. The fourth electron gets paired with the one electron in the T2G level, giving the configuration T2G4. The number of the lone pair of the number of unpaired electron here is 2. The number of unpaired electron here is 4. So this one is the high spin scenario. This one is the low spin scenario. So the strong field complexes, strong field ligands will mainly enhance to produce the low spin complexes. And the weak field ligands will mainly tend towards forming the high spin complexes. So if delta is less than P, the fourth electron enters one of the EG orbitals, giving the electronic configuration T2G3 EG1. Now ligands for which delta is less than P, they are known as the weak field ligands, and that's why they form the high spin complexes. But when delta is greater than P, it becomes energetically more feasible for the fourth electron to occupy a T2G orbital, actually get paired up with the present electron to give the configuration T2G4 EG0. The ligands which are able to produce this effect are strong field ligands, and they form the low spin complexes. In case of the D4 to D7, in every case, such two scenarios will occur, and depending upon the nature of the ligand and the metal, we have to conclude which kind of complex it will be forming, low spin complex or the high spin complex. Now, calculations have shown that from D4 to D7, the coordination entities are more stable in the strong field ligand cases than to weak field cases, in most of the cases, not in case of the all the cases. Now we will come to the case of the tetrahedral crystal field. Now this tetrahedral crystal field is quite different than that of the octahedral field. In case of the tetrahedral coordination entity, the d orbital splitting is actually inverted. It's thus opposite, and the splitting is also smaller than compared to the octahedral splitting. Now, if we can start from the beginning, it is quite easy to understand. Here the d orbitals of the free metal ion are there. Now, in place of a spherical field, the average energy is now going upwards. The average energy of the d orbitals in a spherical field. Now we are having this barycenter over here. Now there we had, depending upon the geometry of the ligand, the tetrahedral field, that dxy, dyz, and dzx, they will be lifted upwards. They are termed as T2. And the dx square, y square, and dz square, which were above the barycenter, because they were experiencing more amount of repulsion from the ligand, they are actually experiencing lower amount of repulsion. That's why the energy here is actually lower. You can see in tetrahedral complexes, there is no center of symmetry. That's why the suffix G is actually omitted over here. There is no G. It is only E and T2. No G is there. So while writing about the tetrahedral complex, please remember this fact. In case of tetrahedral complexes, there should not be any G, because it is lacking at the center of symmetry. And here, since that XY, the ligands are actually pointed on the axis, that's why dxy, dyz, and zx are experiences more amount of repulsion. In case of dx square minus y square and dz square, they are experiencing less amount of repulsion. That's why the splitting is actually here inverted compared to the octahedral field splitting. Rest, all the things are quite similar. They are also in case of E orbitals, the two energies were there 3/5 delta, and here also the T2 orbitals having energy 2/5 delta. But here the notion is delta T, not delta O. You can see in case of tetrahedral splitting, the energy is quite less. it is only 4/9 of the delta octahedral. So 4/9 meaning only 44%. So even less than half of the octahedral splitting. So that's why the delta T is very much less than delta O. Since delta T is very much less, it is very much easy to go to jump from the E to the T2 level. The pairing energy is always more than that of the delta, that is the crystal field splitting energy. That's why in most of the cases, the pairing does not occur and low spin complexes are not observed. High spin complexes are observed. That's why tetrahedral complexes always have, or in the most of the case, have the high spin complexes from high spin ones. Because you can see delta is actually, the pairing energy is there. So pairing energy is actually greater than delta octahedral. So in case of this scenario, if the pairing energy is greater than delta octahedral, then we are having the high spin complexes. Here we are having delta T. Delta T is even less than delta O. That too only 544%. A huge gap is there. So it is more likely that pairing energy will always be greater than, or in most of the cases, be greater than delta T. That's why in case of the tetrahedral complexes, we are seeing the high spins one more. So two factors are there. There should be no I, that is center of symmetry. Lack of symmetry is there. That's why G subscript is not used with the energy levels. And then we are having this high spin complexes. And secondly, which is very much important here, is in case of the tetrahedral complexes, the pairing energy is actually higher than the delta T, because delta T is very much less. The orbital splitting energies are not sufficiently large to force pairing. And that's why low spin configurations are rarely observed. The high spin configurations are the one which is majorly observed. Now we shall come to the part of the color. The color in the coordination compounds. Now the color is actually a very important thing that is found in the coordination complexes. So in previous unit, we learned about one of the most distinctive properties. One of the most distinctive properties of the these transition metal complexes is the wide variety of colors. This means when that some of the visible spectrum is being removed from the white light as it passes through the sample. So the light that emerges is no longer white. The color of the complex is complementary to the one which we are observing. The complementary color is the color which is generated from the leftover wavelength. Now, if green light is absorbed by the complex, it appears red. Now, in this table, we have given the relationship of the different wavelength absorbed and the color observed. So this table is actually important for you to have a look. Here you can see the first compound, which is COCl whole 5 2 plus. Now, wavelength of the light absorbed is 535. Now, let us actually draw here about the color, which is in the visible spectrum, which is the VIBGYOR. This is at the lower end, which is towards the UV, which is 400, and this is the at the higher end, which is 800 in the nanometer region. The wavelength is actually here, nu. So the violet is actually having the 400. You can see the wavelength of light absorbed here is 535. So 535 lies around here, because if you can see this green around 600, the 535 is around here. The light observed is actually becoming yellow, which is in the 650 or 660 region. The color of light absorbed is actually yellow, which is 535. The color of the compound is actually is in the favor of the violet, which is in this side. So absorbing is actually happening in the Y as the yellow region is absorbing, but the color showing is actually violet. The absorbing, this is emitting. So absorbing in the Y region, emitting in the violet region. The next complex, we are having this 500 nanometer wavelength absorbance. That is in the blue-green region. Blue-green region means this region. So here it is the absorbing and the color is actually showing in the red direction. Absorbance here and red here. Next case, the absorbance of the color is actually in the blue. Color of light absorbed is blue, which is in the 475 nanometer. In this case, blue. The color shown is the yellow-orange, which is between this. In the next case, we are having this COCN63-, which is absorbing in the UV region, in the ultraviolet region. And the color shown is pale yellow. So it is absorbing in this and it is showing in yellow. This copper complex is having the wavelength in the red region, which is the 600 wavelength region, red. The color shown is actually here, it is blue. And we are having this titanium 3+ complex, which is having in this blue-green region. Blue-green region means in this region. But the color of the coordination entity is actually in the violet. So here you can see so much mixing up between the light of the color. The absorbance of the light absorbed is actually have to correlate with the color that is shown by the coordination entity. But in this case that I have drawn over the entire table, you can see there is no such correlation. So how we will be able to see which color is shown by which compound? So for this, a very good color wheel is there. This color wheel will tell like how many or which color is actually complementary to which. So depending upon that, we can predict which color is shown by which kind of compound. So let us draw the segment over here. It is in the blue region. This one is the violet region. This one is the red region. This one is the green region. This one is the yellow region. And this one is the orange region. So we are having this color wheel, which is the VIBGY or color wheel. Now, when the color that is actually getting absorbed in the complex will be just the opposite in the complex that will be shown. Or so here, when we are having this color of light absorbed is yellow, now opposite to yellow, it is violet. So that's why the color is actually showing here as violet. We are having blue-green. Now opposite to blue-green, it is reddish-orange. That's why the color is actually red. So depending upon the wavelength of the light that is absorbed, the opposite will be emitted. So that's why the complementary thing is actually written here, which is the complementary color system. Which color is actually absorbed by the wavelength of light is absorbed by the coordination entity, the opposite or the complementary will be emitted. So that will be coming to our, so which color that we are seeing of a complex, the opposite color's wavelength is actually getting absorbed by the complex. In case of red opposite, we can see the blue color is there. So depending upon the nature of the wavelength that is absorbed by the compound, we will have to say which color is actually getting shown by the complex. Now, in case of this titanium hexaqua 3+, it is a typical example which is quite violet in color that we can explain by the crystal field theory. Now, this is an octahedral complex. It is having this 3D1 system. Only one d electron is there in the T2G level, which is in the ground state of the complex. Now, the next higher state of the electron that is available is the empty TG level. Now, if the light corresponding to the energy of the blue-green region is absorbed, the blue-green region over here. So light of the blue-green region is absorbed by the complex. Now it would excite the electron from the T2G level to the EG level. So the electronic configuration shift will be T2G1 EG0 to T2G0 EG1. Now consequently, the complex appears violet in color. Now the crystal field theory attributes the color of the coordination compounds to the DD transition of the system. DD transition meaning it is actually transition between a d orbital to another d orbital from a T2G level to an EG level. Now it is important to note that in the absence of ligand, the splitting does not occur. This is actually sole property provided by the ligand, and then the substance will be colorless. For example, if we can heat titanium hexaqua Cl3, and when the water will be eliminated, then it will be colorless. Titanium H2O whole 6 Cl3, if we can heat and prepare the anhydrous TiCl3, then it will be colorless. So similarly, if we talk about the copper sulfate, which is anhydrous, which is white, but copper sulfate dot 5H2O is blue, because the presence of the aqua ligand or the water ligand is the main culprit behind the showing of the color. Lastly, we will talk about the bonding in metal carbonyls. In some previous cases also, I have discussed a little bit on the metal carbonyl bonding. Now here also the bonding can be actually explained. The homolectic carbonyls. Homolectic means the compounds which are containing only carbonyl ligands, which are formed by majority of the transition metals. You can see nickel CO whole 4, which is tetrahedral, FeCO whole 5, which is trigonal bipyramidal, CrCO whole 6, which is octahedral. So these things are there. Now this decacarbonyl dimanganese Mn2CO10 is made up of 2 square pyramidal MnCO5 units, which is bridged by a Mn-Mn bond. The octacarbonyl dicobalt, which is having this CO-CO bond bridged by 2 CO groups. So, which are actually monovalent metal carbonyls. We have also di metal carbonyls also. If talk about this Mn2CO10, a metal bond between 2 Mn atoms. We are having 5 COs each attached to every Mn atom. Here, if we can talk about the cobalt octacarbonyl, icobalt octacarbonyl, we are having these 2 cobalts. Now 8 such carbonyls are there. 3 will be terminal and 2 will be bridging. CO or carbonyl is a very good ligand which is able to bridge between 2 metal centers. There is also a metal bond between 2 cobalt atoms. Here the other things are CO. Now let us typically find out which kind of bonding is present in the metal carbonyl. Now I have drawn a typical picture for you guys reference to see which kind of bonding is present in metal carbonyl. This metal carbon bond in metal carbonyl possess both sigma character and pi character. Both sigma and pi characters are present in metal carbonyl. The MC sigma bond is formed by the donation of lone pair of electrons on the carbonyl carbon into a vacant D of a metal atom. Here you can see this is the sigma bond that is actually forming between the CO and the metal. There is a sigma bond formation between the CO lone pair and the metal vacant d orbital. Now the MC pi bond is formed by the donation of a pair of electrons from a filled d orbital of metal into the vacant antibonding pi star orbital of the carbon monoxide. Here it is the pi bond. Here you can see from the metal center, which is the filled pi or electrons are actually going towards the vacant anti-bonding pi star orbital of the CO. Now, since the ligand to metal and metal to ligand back bonding is there, which is creating a strong synergistic effect, which is strengthening the bond between the metal and the CO, which is termed as the synergic bonding. Synergic bonding means when the CO will actually will bond to the metal first, and the metal's extra electron density will be again driven back to the CO, which is called as the back bonding. These two things are operating simultaneously, hand in hand. That's why the bond between the metal and CO is so much strong in nature, and that's why it is called the synergic bond. So with this, we will draw the conclusion to the coordination compounds, and that was all in your for your NCERT syllabus, where the specific things have been discussed: the geometries, the color, the coordination chemistry, and everything. So with this, we will draw the conclusion to this class. Thank you.